Welcome everybody. With this set of videos, we're looking at topic 15.6, the concept of Compton scattering. Thanks for joining me. I'm Holly Mosley and I teach at Liberty High School in Frisco, Texas. Let's get started with a little bit of a review of what we already know about light. So in topic 15.1, you learned that light can be modeled as both a wave and as discrete particles called photons. Photons travel in straight lines unless they interact with matter. A photon is massless and it's electrically neutral, and the energy of a photon is directly proportional to the photon's frequency. So remember, there's an inverse relationship between the wavelength of the light and its frequency. So if the energy of the photon is proportional to the frequency and the wavelength is inversely proportional to the frequency, then the energy of a photon is inversely proportional to the wavelength. Also in topic 15.1, you learned that particles can demonstrate wave properties, and the wavelength of those waves is equal to Planck's constant divided by the momentum of the particle. So let's put all of this together and look at an example. So in this example, a photon approaches an electron at rest as shown, and it collides elastically with the electron. After the collision, the electron moves towards the top of the page and to the right as shown at a known speed and angle. We're asked to do two things in this scenario. First, indicate a possible direction for the photon that exists after the collision, and second, to indicate the photon's frequency compared to that of the original photon. So before we go any further, I want to note that it's not the same photon. We get a new photon as a result of this collision. We're also asked to describe the application of the physics principles that can be used to determine the direction of motion and the frequency of the photon that exists after the collision. So let's dig a little bit deeper into this question. First of all, the photon approaches the electron. So the photon is moving, and we're told the electron is at rest. The photons collide. So let's start there. Anytime we're dealing with a collision, we're dealing with conservation of momentum. Momentum is conserved as long as there are no external forces. Also, the collision is elastic. So when a collision is elastic, that means kinetic energy is conserved. So keep that in mind. So before we go a little bit further, let's take this opportunity to review collisions. Like we just said, an elastic collision between objects is one in which the initial kinetic energy of the system is equal to the final kinetic energy of the system. However, while the total kinetic energy of the system is constant, that doesn't mean each individual object's kinetic energy is constant. It means those individual energies can change, but the total is constant. So let's look at this from an energy bar chart. So we're going to model this system as it undergoes the collisions using an energy bar chart. Before the collision, the photon has an energy equal to Planck's constant times its frequency. That's a non-zero number. I've chosen to represent that here with 4 units of energy. The electron isn't moving, so it doesn't have any energy. After the collision, though, the electron is moving, so it has some kinetic energy. We don't know how much. So I've opted to depict that as 1 unit of energy here. Now, since the collision is elastic, the total energy before the collision is the same as the energy after the collision. So that means the energy of the photon after the collision would be less than before the collision. So I've shown that here as 3 units so that I have a total of 4 units of energy. Now let's look at this from a momentum perspective. In the absence of net external forces, any change in the momentum of an object in the system must be balanced by an equivalent and opposite change in momentum somewhere else in the system. That's conservation of momentum. Remember that momentum is a vector quantity and it has the same direction as the velocity. So the photon is initially moving to the right, so it has a rightward momentum, and the electron has no momentum. So let's add a coordinate system so that we can better describe the momentum of the system. So using our new coordinate system, we can see that the photon initially has momentum in the positive x direction. After the collision, we see that the electron has a momentum in both the positive x direction and the positive y direction. So we can apply that same idea of conservation of momentum using a bar chart as well. So let's model only the momentum along the x-axis. The photon has a positive momentum and the electron has no momentum. After the collision, the electron has some momentum in the positive x direction. And since there were no external forces, the momentum has to be the same before and after the collision. So the x component of the photon's momentum would be less than the initial value, which I've shown here. Now let's apply that same model along the y-axis. Before the collision, neither the photon nor the electron had any momentum along the y-axis. After the collision occurs, we see that the electron has some momentum in the positive y direction. And because momentum has to be conserved, that means the momentum of the photon must have a component in the negative y direction. So let's practice putting this all together to answer the question. So looking at the question again, we're asked to do two things: indicate the possible direction and frequency. So we have two things we're indicating. And then we're also asked to describe the physics principles that are used to support our answer. So let's put all of this together and see what an answer to this could look like. So before we jump straight in and just give an answer, let's lay out the components of the argument. So when the photon collides with the electron, energy is conserved. The electron's energy increases because of the collision, so we figured out that the photon's energy must decrease. And we said at the start of the video that the photon's energy is related to its frequency by E equals hf. So that means the frequency of the photon must also decrease. Now we've answered the first part of the question, but let's take it one step further just because we're practicing and we're learning this. Since the wavelength of the photon is related to its frequency by wavelength equals speed of light in a vacuum over frequency, another thing that happens is that the wavelength of the new photon is greater after the collision. All right, let's talk about the momentum now. When the photon collides with the electron, we know the momentum is conserved. The initial momentum of the photon-electron system was only in the positive x direction, so the final momentum must also only be in the positive x direction. Because the electron had a component of its momentum in the positive y direction, that tells us the photon must have a component of its momentum in the negative y direction. So what should we take away from this video? In Compton scattering, a photon interacts with a free electron. The Compton effect is when a photon that emerges from that interaction has a lower energy and therefore longer wavelength than the incoming photon. Momentum is conserved in the collision between the photon and the electron because there's no external forces acting on the system. And lastly, energy is conserved in the collision because it is an elastic collision. Thanks for watching. See you next time. Welcome everybody. Let's continue our discussion of topic 15.6, Compton scattering. In this video, we're going to use conservation of momentum and conservation of energy to describe and predict the results of an interaction between a photon and an electron. Thanks for joining me. I'm Holly Mosley and I teach at Liberty High School in Frisco, Texas. Let's start out with some review. So in this video, we're going to take a more quantitative approach, but in the last video, we looked at the principles that guide the behavior of a collision between a photon and a free electron. So this first question is going to allow us to review those concepts. So in this example, a photon scatters from an electron that is initially at rest. We want to know which of the following is true of the wavelength and frequency of the scattered photon compared to those of the incident photon. So we have an incident photon that's about to collide with an electron, and we can see that the scattered electron kind of travels up and to the right, and the scattered photon is down and to the right. And so we need to figure out what we can say about the wavelength and the frequency of the scattered photon. So is it A, that the wavelength is greater and the frequency is less? B, that the wavelength is greater and the frequency is the same? C, that the wavelength is less and the frequency is greater? Or D, is it that the wavelength is less and the frequency is the same? So the electron is initially at rest. So let's remember that. We know that the wavelength and frequency of a photon are inversely related by wavelength equals speed of light in a vacuum over frequency, where speed of light in a vacuum is a physical constant. So right away, we can eliminate choices B and D because they don't show an inverse relationship between wavelength and frequency. The wavelength can't be greater while the frequency remains the same, or the wavelength can't be less and the frequency remain the same. So those are out. So now we also know that the energy of the photon is related to its frequency by energy equals Planck's constant times frequency. Since the electron is moving after the collision, we know that energy is transferred from the photon to the electron in the collision, meaning that the energy of the scattered photon is less than the energy of the incident photon. Since that energy is less, the frequency must also be less, and therefore the wavelength would be greater. So let's look at another example. This time we're actually going to do some calculations rather than just comparing quantities. So in this example, a photon with 3 times 10 to the minus 14th joules of energy collides with a free electron at rest. After the collision, the electron travels in the same direction as the photon's initial direction at a speed of 1.67 times 10 to the 8th meters per second. We want to know the direction of the photon and the wavelength of the photon that emerges from the collision. So let's look at some mathematical models for photon momentum and energy. We know that photon momentum is inversely proportional to the wavelength by the equation momentum equals Planck's constant over wavelength. We also know that photon energy is equal to Planck's constant times frequency, and frequency is speed of light in a vacuum over wavelength. So that means photon energy is inversely proportional to wavelength. So let's solve that above expression for wavelength, and we get that wavelength is equal to Planck's constant times the speed of light over energy. Lastly, when we substitute hc over E for the wavelength in the momentum equation, we get that photon momentum is proportional to photon energy by momentum equals energy over speed of light. So let's use these relationships to solve our example problem. Let's start with the first question, the direction of the photon after the collision. So we know that momentum is conserved in the collision, so the initial momentum of the system equals the final momentum of the system. The momentum of the system is all along a single axis. It's all along the x-axis. The momentum of the photon plus the momentum of the electron before the collision has to equal the momentum of the photon plus the momentum of the electron after the collision. So we can substitute in that expression that we just derived on the previous slide for the momentum of the photon before the collision. And then the momentum of the electron before the collision is 0 because it's not moving. Now we want to know the momentum of the photon after the collision, and the momentum of the electron after the collision is equal to the product of the electron's mass and its velocity, just like you learned in Physics 1. So we can solve this equation for the final momentum of the photon, and then we can substitute in the known values for the energy of the photon and the speed of light, as well as the mass and the speed of the electron. Remember, mass of an electron is on your table of information. And we get that the momentum of the photon is negative 5.21 times 10 to the minus 23rd kilogram meters per second. Since we designated right as positive when we substituted in the speed of the electron as a positive number, the negative indicates that the photon emerges from the interaction moving to the left. Now let's calculate the wavelength of the photon after the collision. We can start with that relationship momentum of the photon equals Planck's constant over wavelength. Solving for wavelength, we get lambda equals h over p. Substituting in Planck's constant and the magnitude of the momentum from the previous calculation, we get that the wavelength of the photon is 1.27 times 10 to the minus 11th meters. So what should we take away from this video? In Compton scattering, momentum is conserved in the collision between the photon and electron. Remember that momentum is a vector quantity. And the momentum of a photon is given by P equals h over lambda or E over c. And the momentum of a particle with mass, like our electron, is still mass times velocity. Thanks for watching. See you. Welcome, everybody. We're going to continue our discussion of topic 15.6, Compton scattering. In this video, we're going to use conservation laws to relate the change in a photon's wavelength when a photon interacts with an electron to the direction change of the photon. Thanks for joining me. I'm Holly Mosley, and I teach at Liberty High School in Frisco, Texas. So let's start with some review from our previous videos. In the last video, we calculated the wavelength of a photon that emerged from a collision between a photon and an electron. We first calculated the momentum, and then we used the magnitude of the momentum to calculate the wavelength of the photon. If you need to, you can go back and review video 2 from topic 15.6. Let's look at another example. So this equation here mathematically models the change in the wavelength experienced by a photon after colliding with an electron. This equation is derived from conservation of momentum and conservation of energy concepts, but note that you would not have to derive this equation. This is given on your equation sheet. So the quantities h, me, and c are all physical constants. So Planck's constant, mass of an electron, and speed of light in a vacuum. They're all physical constants. So this equation relates the change in wavelength of the photon to how much the photon's direction changes. So theta is the angle between the initial and final momentum of the photon. So the angle between the initial and the final momentum of a photon is often called the scattering angle. So if the photon continues in the same direction after the collision, then the scattering angle would be 0. The photon could also be scattered at an angle less than 90 degrees. Photon could be scattered at an angle more than 90 degrees. That would look like this. Or the maximum possible scattering angle is when the photon ends up traveling in exactly the opposite direction. And so that scattering angle would be 180 degrees. So let's practice. We're going to apply this concept to the same example problem we worked in the last video. This is the same example from video 2. So let's start with our new equation. The change in wavelength equals h over the mass of the electron times the speed of light times 1 minus the cosine of the scattering angle. We'll substitute Planck's constant in joule seconds so that we can match up our units, the mass of the electron in kilograms, and the speed of light in meters per second. Because the photon emerged from the collision traveling in the exact opposite direction, the scattering angle is 180 degrees. So therefore, the change in the wavelength is 4.85 times 10 to the minus 12 meters. Adding this change to the initial wavelength of the photon, which can be calculated from its initial energy, gives a final wavelength of 1.15 times 10 to the minus 11th meters. Now, I do want to point out this number is a little bit different than the value that we calculated using the other approach, but not much, just a little bit. So you probably know when a mathematical model doesn't predict the exact physical outcome of a scenario, sometimes the model needs to be refined to address additional factors. For example, like in physics 1, if you launch a projectile off a cliff, our mathematical model may not actually predict the exact landing point where that object is going to land. We might need to refine our model and address other factors like drag. But that would be beyond the scope of physics 1 and 2. In the same way, we do have a little bit of a disagreement here because there is another factor. There's some relativistic stuff going on because this electron is moving so fast that we would have to consider. But just like drag, this is beyond the scope of our course. So you wouldn't be expected to refine that any further. So those are really, really close, and they're close enough for physics 2. So what should we take away from this video? So the change in wavelength of a scattered photon is given by the mathematical model delta lambda equals h over mass of the electron times c times 1 minus the cosine of the scattering angle. Remember, h, mass of electron, and c are physical constants, so the change in wavelength only depends on the scattering angle. Thanks for watching. See you next time.